Good morning, everyone. My name is Ben Pellegrini, and I'm co-founder and CEO at Intelligence. Firstly, I'd just like to thank the APC for inviting me here today to talk to you about how we are using machine learning to help design better materials, chemicals, and drugs faster, cheaper, and cleaner than ever before. We're a spin-out from Cambridge University using a new type of machine learning to really accelerate and improve current R&D processes in three key ways. Firstly, we can reduce the number of expensive and iterative experiments by around 90%, saving both time and money. Secondly, we can reduce the reliance on expensive or toxic components. Can we design materials and chemicals with the same physical characteristics, cheaper and cleaner, with machine learning? And finally, standardizing a data-driven approach to these material and chemical design problems. This data-driven approach, which machine learning really is, means that information and decision-making can be made more transparent. Today, I'm going to talk very briefly about the type of problems we are working on, and then what this process looks like in practice. And finally, I'll talk through two real-world problems where machine learning has delivered significant benefits over traditional material and chemical design. So firstly, looking at the types of problems that Intelligence is trying to solve with machine learning, we are looking at ways to improve industrial formulations or industrial recipes. And we can see in this diagram some of the general principles or the big picture of how we think about these processes. Starting on the left, we have our raw ingredients, which could be elements in a material or molecules in a chemical. And then we have the processes applied to those ingredients. How are these ingredients put together? What temperatures or pressures do we use? And then finally, on the right, we have the output, the final material with certain physical characteristics, such as strength, cost, weight, etc. And what we're always trying to do in material design problems is understand how we go from these ingredients and processes to a set of desired target properties. Our machine learning enables a generic methodology to handle these type of problems and develop new materials and chemicals as efficiently as possible. So now we know the type of problems that we're looking at Intelligence, these industrial recipes or these industrial formulations. What does this look like in the real world? If you go back to your office or lab when you're allowed, how can you practically use this approach? What does the data look like? And the data is really key for good machine learning models. So on the screen here, we have a typical data set that we might work with and could hopefully be used to guide the design of a new steel in the future. What we are looking at here is perhaps a small section of a much larger data set that could be hundreds, thousands, or millions of rows with hundreds or thousands of columns. Each row represents a different material, in this case a steel, and the columns show different parts of the formulation. Again, on the left, we have some composition information, such as iron and carbon. We then have a process column, which shows the heat treatment applied. And then finally, we have the three physical properties of the material. We can immediately see this data is typical of real-world experimental data. Inconsistencies in data recorded, some experiments completed on some steels and not others. However, we can apply machine learning methods to this data as it is now. Firstly, we could predict all the missing values, which in itself can save significant time and reduce the need to retest known materials. But more importantly, now we've generated a model from this data set, we can start asking it some questions. The main question we want to ask from a material design perspective is, given a set of targets or desired outcomes, tell me how we can make it. What does the rest of the recipe look like? Here we can see we have set a tensile strength and a yield strength, and we've also set a desired value for manganese. Given these targets, can the model now go away and suggest to us how that can be achieved? And on the final step here, we can see that the rest of that recipe or that formulation has been proposed. Now, there are some subtleties around how we can ask this question. For example, do we want a material that will just about satisfy our targets? Or do we want a material that potentially extrapolates a long way from the existing data and provide a potentially domain-changing material with stellar physical properties that has the potential to be a lot less likely to work? So now I'd like to share a couple of real-world examples of where this generic machine learning approach has been applied and delivered real-world savings. The first use case I'd like to talk about would be for the design of high-performance alloys in aerospace. In this case, a new alloy was needed for use in the jet engine that we can see here. In this particular case, we needed to find a new alloy that can not only survive at extremely high temperatures, but it must also not oxidize or corrode in the environment it is being used. It must be tough to survive impact from a bird, light enough so the plane can take off, and cheap enough to make it commercially viable. In other words, a whole range of physical targets that need to be achieved for this alloy to be a success. Traditional trial and improvement approaches to this type of problem, looking at improving perhaps one or two properties at a time, will result in significant timescales where each design and test cycle could take many months, and often improving one property can negatively impact others. Finding the sweet spot between all the target properties is especially challenging and can often take up to 20 years in problematic domains such as aerospace. Machine learning can overcome this by using historical data combined with first principle simulation to understand the underlying correlations in this data and deliver models that can propose new alloys in a fraction of the time. In this case, a new nickel-based alloy, superalloy, was proposed that achieved the 11 target properties set. It was experimentally verified and patented, the whole project taking less than 1.5 years, reducing the development costs by around $10 million. The second application area I would like to talk about is the area of battery design and optimization. New batteries are critically important to help deliver the next generation of energy sources, moving away from fossil fuels and enabling new, cleaner propulsion systems. When designing these new high-performance batteries, there are a number of target properties we might want to consider. Can we get the batteries to store more charge so that the vehicle will have a greater range? Or can we get them to charge quicker so you have to plug them in for less time? Can we create lighter batteries to enable better performance? And could we lower the cost or improve the safety of the batteries? These represent a number of big challenges that will require new materials and chemicals to be designed, tested, and manufactured. We could, of course, use this machine learning approach to help optimize one or more of the material systems in use in the battery. Perhaps we could look at the cathode or the anode or the electrolyte individually by using the models to run virtual experiments, tweaking their compositions or the treatment processes to deliver better results. But we may also want to try and model the battery system as a whole to provide both future predictions and real-time information relating to things like useful life, state of health of the battery, and state of charge. Finally, we could use this type of machine learning to help improve battery fabrication processes to enable the delivery of more reliable products. In all of these cases, the same underlying machine learning methodology has been used to optimize results while reducing costs. We've also applied this same generic methodology in a number of other real-world domains. And just to highlight a couple more in the remaining minutes I have here, we've recently completed a small molecule drug discovery competition for antimalarial drugs, where this industrial formulation technology was used to guide the design of a new compound against a novel antimalarial mechanism of action. In additive manufacturing, machine learning enabled design of new alloys for use in 3D printing, where processing conditions can have a significant outcome on the product quality and reliability due to the repeated heating and cooling processes involved. And finally, in construction, CO2 generated in cement production accounts for around 8% of global emissions. Can we use machine learning to explore new chemistry to reduce this CO2? And also, could we deliver products to construction sites more efficiently? So in summary, I hope this gives you an idea of how we at Intelligence are using machine learning to deliver real world value. And more importantly, how machine learning is enabling the next generation of materials, chemicals, and drugs to be designed faster, cheaper, and cleaner than ever before. And that's me. Thank you very much for listening.